Okay, so we've managed to not get rid of, but find an expression for the first term. Recall this is our mass matrix. Now we can do the same for our stiffness matrix. So again, from dynamic conventions, we call this the stiffness because it's with respect to derivatives in the x direction. So you could see that if you had some sort of spring in a mass spring system, changes in the length of the spring are related to the stiffness of the spring. So similar to the mass matrix, we can substitute our approximation and weighting bases into our stiffness term. And similarly, because our coefficients on our approximation bases are again not with respect to space but just time, we can pull them out of the integrand. Now notice we have this additional term here, c, and that's a consequence of the flux. So because we have constant flux, this is a very simple term to relate, but so our flux with respect to q is just going to be simply cq. So you could even put your velocity on the outside of the sum as well. So we get something that looks very similar, at least overall, to the integrand for the mass matrix, but notice we have one key difference. We still have our solution basis appearing here, but now we have the derivative of our weighting basis here. And recall that we swapped the derivatives by the integration by parts. But we still have analytical relations for each of these bases, so we can certainly perform that differentiation and then look at what the result of the integral would be. So let's take a look at what we would do for this simple case. So again, we can imagine that we have some vector of our coefficients on our solution approximation. Now it's just the coefficients themselves, not the derivatives with respect to time. And we can multiply that by our stiffness matrix. So again, we imagine that we have our solution approximation, or solution bases moving in this direction, so that when we multiply by that row vector, we recover the actual solution at each of the row values. And actually, if you notice, this should have a c in the front of it. So let's substitute in our expressions and see what we get out. So again, we're doing this for the zero term for our weighting bases. So if we look at, let's say, our bases for, and I'll do it down here to make it a little more clear. So let's look at the zero term for our solution bases. Well, so what is it? And this is going to be the, again, abusive notation, but, well, it's going to be the integral of 1 minus x. Now, the underlying term is 1 minus x as well, but we're differentiating that with respect to x. So that's just going to simply be 1, or, well, minus 1 rather. And then we can do this for, oops, this should be 1. The other one for the 0th weighting bases. And let me correct my notation here. And so we can see that this is going to be x times, now it's the same expression, so it's just going to be a minus 1. And now we can do this for the first, the one term for our weighting bases, and again differentiated, and we'll write the other one in here too while we're over here. And so again, no surprises here, we have our 1 minus x, but now we have a different weighting bases. This is going to be our positive x, so that's just going to be simply a positive 1. And we have our x, and again, just a positive 1. And so we're integrating this again from 0 to 1. Okay, so when we look at the, when we perform this integration on here, we can see that we would get minus a half and minus a half, thanks to this minus term here, and then a half and a half. So notice in this case this is not symmetric.